Y'all doing okay today? Yeah? No? Tired?
I have a job interview this morning.
You had a job interview? Do you want to talk about it? Do we need to have a little therapy session? We can. Did it not go well? You got the job? And then what?
I turned it down.
Oh, you turned it down.
Because they were only going to hire me for 3 weeks, but I had to be there like all day, every day for the 3 weeks.
And then what were they going to do after 3 weeks?
Out of the 50 of us that they hired, they were going to decide which 10 of us they were going to keep.
Oh,
And I said,
yeah, that's no good. So I guess, yeah, well, go look for another job, I guess, right?
I have another interview tomorrow.
Okay. All right. Yeah, so, you know the daughter I've told you all about with the clothes and stuff? She got hired. She got a job at SeaWorld, being a lifeguard. So if you go to SeaWorld, be careful. Don't leave your kids unattended. No, I'm kidding. They don't let them have their phones while they're lifeguarding. So I think that's gonna. They do not.
Oh.
I was surprised. Does that surprise you? It surprised me. It surprised me because I would think someone would have said, well, we have to have our phones because what if there's an emergency? Yeah. It's 2019. I mean, it wouldn't surprise me if a lifeguard had their phone. But anyway, I'm kidding. Yeah, we'll see how she does. I don't know if she'll like being in the sun during this summer. But okay, we're going to talk about exponential functions. I don't know how to say this to you all, but you know, I'm looking at the notes, the packet, you know, and it's just like, it's so difficult for me to stand up here and try and teach out of that packet because it's like, Robert, what do you like, Robert? Is there something that really you're interested in? Can I ask you that? No? No? Someone give me something that they have a passion for, that they really like. Football? Okay, so if I were to, like someone who doesn't know football, if I were to say, football, it's just these guys, they just run up and down a field. Like that doesn't really encapsulate what football is, right? So take anything that you like and imagine someone describing it in the most like ridiculous way that doesn't really give it the full credit. That's what I've pretty much had to do this entire semester with everything we're doing. And especially with exponential functions. Like I'm supposed to teach this in one day, and it's guys running up and down a field. And I can't do that. So I'm going to try at least a little bit to show you a glimpse into what these functions are a little bit without going too much off the rails. But just understand I'm like restraining myself from going off too much on this, all right? Okay? Yes, question, comment? Pardon? A review for the test next week? Yes. Yeah. This will be the last topic on the test. Okay. All right. And you know what? I'll try and put a review together that I will email out so you have it for the weekend. Okay? That sound good? Okay. Our test, right? Is it next Wednesday, right? Okay. I'll email out something for review so you'll have it for the weekend. I don't want to give it to you on Monday and only leave you 2 days with it. So let me do that. If you don't see it by Friday, somebody send me an email and be like, where's my review? All right? All right, so exponential functions. Let's start first with an example that I think most people can follow. Let's say that we have, I'm going to call this the bacteria example. Do y'all know what a Petri dish is? Yeah. Petri dish is like this little dish that's completely clean of anything, right? It's like, what do they call that? Sterile, right? So you have a sterilized dish, and then you I don't know, you go and you rub your finger on the door handle and put it in there, or like swab it. Put in there, close the dish up, and come back a week later and you look in there and go, oh my God, what happened, right? So then you look at what was in that dish. And that's usually some sort of bacteria that's growing. And so bacteria, the way the bacteria grows is that it starts off maybe with, let's just say, a single bacteria. So I'm just going to put a little happy face on that little guy, that one bacteria. And then what happens is that bacteria will duplicate. It'll split off and become 2. Sometimes it'll split and become 3, depends on the bacteria. But let's say for this bacteria, it splits off and becomes 2. And let's say that takes, how long do you want that to take for it to split? You want to go with a day? Let's just say a day. It might be an hour. It might be, 10 minutes. Depends again on the bacteria. So let's say it takes 1 day for that to happen. Right? And then how many bacteria are you going to have after 2 days? So this guy's going to split, right? And this guy's going to split. So now you have how many here? So you start with 1. A day later you have 2. A day later you now have 4, right? Yes? Then what's going to happen? This is after 2 days, right? What happens after 3 days? How many will you have? Each one splits off. So 1, 2, 3, 4, 5, 6, 7, 8. No, we're not counting all of them because this one's no longer here. He split into 2, right? That one split into 2. So this is actually how many are there, all right? So we're not doing a cumulative addition of these. All right, understand? So the question is now, how many will be there after, let's say, a week? How would you figure that out? Well, you could just keep drawing, right? Go, 3 days. Now, next one would be, this is after 3. The next one would be 4, 5, 6, 7. You could draw the dots and then count them, right? You could do that? Right? Now, what about after 2 weeks, 14 days? Would you really want to draw all those lines out and try and figure it out? You wouldn't, right? So the question is there a function that when I plug in x, and let's say x is the number of days, is there a function that when I plug in x, the number of days, it will spit out the number of bacteria that are there? Does that make sense? So almost like this, a t-table where here's the days and here's the number of bacteria. So let's fill out this table for what we have. At 0 days, how many bacteria are there? 1, right? So when no time has passed, we put that 1 bacteria there, we have 1 bacteria, right? So at 0 days, 1. How about after 1 day, how many did we have? 1, 2, right? After 2 days, we had 4. After 3 days, we had 8. What would we have after 4 days? So if each of these doubled, right, you would have 16. Do you see a pattern here? It's doubling each time, isn't it? So what will we have after 5 days? 32. But my question is, what would we have, let's say, after 10 days, but I'm not allowing you to keep going down this chart. Like, plug 10 into some function and see what it spits out. So can we look at this and see if we can come up with a function? Is it any, like, it almost looks, if you just look at these two, doesn't it look like we're just doubling? Like you plug in 1, multiply that by 2, what would you get? 2. Take in 2, double it. What would you get? 4. Take in 3, double it. What would you get? Doesn't work. Do y'all see that? So how about x squared? Okay, so what happens if I square 1? 1 squared is 1, right? Now 2 squared is 4, but 3 squared is not 8, it's 9. So x squared won't work. Do you follow? I don't know who said that. I just heard it come from over there. So you see x squared won't work? Do y'all agree that 2 times x won't work? So let me put those up here. We thought maybe it was this, or maybe we thought it might be this. And do you all agree that neither one of these would work? Yes? Is there something that works though? So I'm going to show you something and just see if you agree with me. Do you all agree that this is 2 to the first power? Do you all agree that that's 2 squared? Yes? Do you agree that this is 2 cubed? 2 times 2 times 2. Do you agree that this is 2 times 2 times 2 times 2? And this one is 2 times 2 times 2 times 2 times 5 times, right? And do you notice that the exponent is actually what's being plugged in, right? Here, it works, it works. Now what about this though? What would it have to be if it follows this pattern? What would this need to be? 2 to the what? 0. Now, is 2 to the 0 1? Yes. Any number to the 0 is 1. All right? Any number raised to the 0 is 1. So this actually works, doesn't it? So what would my function need to look like? The input, right? Yes, it would have to be the 2 here, and then the x would have to be up here, right? It's not like this where the x is on the bottom and the 2's up here. It's like flipped over, isn't it? It's 2 raised to the x. Yes? So the variable x is up in the exponent, isn't it? And not down in the base like this. The x here is in the base, here the x is in the exponent. Because of this, we call this an exponential function. Any function where you have a number down here and your variable x up on top classifies as an exponential function. All right? Do you see the difference between the two? Between these three? See the big difference between these? Where the x appears up in the exponent? So this should do it. So tell me, after 14 days, how many bacteria are there? After 14 days. We'd have to go 2 raised to the 14th power. So on your calculators, why don't you try and see if you can use your key. Oh, by the way, you really are going to need your calculators the next few classes. So somewhere on your calculator, do 2 raised to the 14th power and tell me what you get. Anyone? Anyone? You got it? Go ahead. 384. 16,384 bacteria will be there after 2 weeks. Okay? Now, what about after a month? Let's just go with like 4 weeks. Let's go with 28 days. What would you get after 28 days? That's 2 to the 28th power. And I want you to notice something. We have 14 days, we have this many, right? 28 days is twice as long, right? Are we going to have about twice as many bacteria? Let's see, 2 to the 28th power. What are you getting? Anyone? 268? 435? 456. That is 268,435,456 bacteria. This is a very rapid rate of growth, isn't it? I mean, look, after 2 weeks, you went from 1 bacteria. After 2 weeks, you had 16,000. So yeah, that's pretty rapid. But look, 2 weeks after that, 268 million. So this type of function grows very rapidly. And that's why when you watch the news, or if you just turn on the TV, I promise you, if you watch like 4 hours of TV, you'll hear someone say exponential growth. Or they'll say something about exponential, you know? Especially in the news. They love throwing that word around, exponential. And it's supposed to imply a rapid rate of growth. All right? So that was the function 2 to the x. Let's take a look at another function. So that's one example of an exponential function. F of x equals 2 to the x. So the next one, I need somebody who's willing to, well, never mind, I have a piece of paper over here. I can use that. Next example is the folding paper problem. So I'm going to take this standard sheet of paper here. What I'm going to do is I'm going to start folding it, and I want you to tell me how many rectangles you see, all right? So right now, I'm not going to fold it. There's 0 folds in the paper, right? How many rectangles do you see? 1. Okay, so let me see here. Folds, rectangles. If I do 0 folds, I have 1 rectangle. What if I fold it once, okay, and then open it back up, and along that fold, I'm going to draw a line so you can see it. How many rectangles did I create by folding this? 2, right? 1 fold, 2 rectangles. Now, I'm going to do it again. Fold once, fold second time. When I open this up, how many rectangles are you going to see? 4? 3? So, can you all see that? How many are there? 4? So 2 folds, 4. Okay, I'm going to do it again. 1 fold, 2 folds, 3 folds. What am I going to get? What do you think? Can you all see that? Looks like we have 4 across the top, 4 across the bottom. So we have 8. So 3 folds, we have 8. Doesn't this look exactly like the bacteria? So I'm going to fold it now a 4th time. Okay, and then I'm going to open it up. How many will we see? 16. I have 4 across the top, 4 down the side. That's 4 times 4, it's 16 boxes. Okay, so how many rectangles would I have if I could fold it, let's say, 13 times? So I'm going to continue this table over here. What if I had 13 folds? How many rectangles would I see? How many? 8,000? 8,192. Okay, so I heard someone say you can't fold. Who said that? You can't fold over a certain number of times? Yeah, so there's have y'all ever heard that? If you take a piece of paper, there's like a maximum number of folds you can make in it. Have y'all ever heard that before? Have you ever seen that that show Mythbusters? I think they tried that in there. They took like a huge piece of paper and like an aircraft hangar, and then they folded it and then got a steamroller and rolled over it and then folded it again, steamrolled over it, and they tried to get past the maximum, which I think 13 is what they were able to get to. I don't remember. But let's see how many we can get. Let's see. So 1 fold, 2 folds, 3 folds, 4, 5. Okay. Let me go with 6 here. 6, that was pretty tough. 7, I don't think I'm going to get to 7. I might get past 7. All right, maybe I could argue I've got 7 here, but I'm not getting past 7. All right, so the idea is that no matter how big your paper is, no matter how thin it is, you can only get 13 is like the max that they've been able to get. Why though? Let's think about this. All right, so when I don't fold it, I have 1 page, right? So this is 1 page thick. When I fold it 1 time, how many pages thick is it? 2 pages thick, right? When I fold it the 3rd time, how many pages thick is this? 8, right? So 1 fold, it's 2. 2 folds, now I have 1, 2, 3, 4 pages thick. When I fold it again, now that doubles, so I'm up to 8. And when I fold it next time, I have 16 pages thick. If you could fold it 13 times, how thick would that be? 8,192 pages. Y'all know what a ream of paper is that you put like in a copying machine? Y'all know how many pages come in a ream? Is it 500? I thought it was 300. 3 to 500. Let's just, yeah, different size. But how many reams of paper is this? You know, this is like 16 to 20 reams of paper. That would be like a stack of paper this high, right? So what you're trying to do is when you fold over, this edge right here has to be as thick as that right there. So it's got to be 18 or 8,000 pages thick. You're basically going to start running out of paper is what happens. And you can't get past a certain number. It's like physically impossible. But theoretically, we could, in theory, we could fold this 18 times. In theory, we could, right? And we know what the answer would be because we just use 2 to the 18, and we would have whatever that is, okay? So this is just another example of exponential growth. Let's do something else that doesn't act like this, because I don't want you to get the idea that every exponential function is 2 raised to the x, because it's not. So I'm going to do a different example. This time I'm going to cut the paper. So here I'm going to say cuts, and then here I'm going to say length. So I'm going to take this sheet of paper, and just to make our life easy, oh, I should put here that this is 2 to the x, right? That's the function that does this over here, right? Same function from before. Okay, so for this one, let's just imagine, act like this is 1 foot long, all right? This is 1 foot from here to here. It's 1 foot long. Now I'm going to start cutting this paper. So right now I have 0 cuts. How long is the paper? 1 foot. Okay? Now I'm going to cut it in half. Now just imagine that I did a perfect cut right down the middle. Okay? And I'm going to get rid of 1. Okay? So I've cut this thing in half. How long is it now from here to here? 6 inches or half a foot, right? So I'm going to put, after 1 cut, I'm half a foot. Right? Now, what if I cut it again? That in half. How long is this? 1 what? 1/4 of a foot, right? Let me bring them all back together here. Here was the one. There's that one, right? So we cut it in half first, right? So we had half, and we did half of that, so half of a half is 1/4. What if I cut it again? 1/8. So that is 1/8 of the page. And if I cut it again, I would get what? 1/16. And I could keep doing this, right? So what if I cut it 13 times? I would have 1 over what? So look at your table over here. Do you see a relationship between this and that? Instead of having 1 and 2, we had 1.5, right? 2 and 4, we actually have, wait a minute, hold on. I messed this up. This was 1/4. I forgot to put the 1/4. Sorry. This was 1/8. 1/16 would be the next one. So what, do you see how these match up? It's just basically this with a 1 on top, isn't it? So if I cut it 13 times, I should have 1 over 8,192. That's how tiny it is. What is the function for this one, though? Can we come up with the function for this one? We know it's something to the x. It's 1/2 to the x. Good. It's 1/2 to the x. So let's just check it. If I plug 0 in, 0 here, 1/2 to the 0 gives you 1, right? If I plug in 1, 1/2 to the 1 gives you 1/2. If I plug in 2, then 1/2 squared is 1/2 times 1/2, which is 1/4. And then, do y'all see how this works? Y'all got it? So this is an example of another type of exponential function. So now let's get to a general definition. One of the main points I want you to take away from this is that there are things that you can look at in the real world that do not behave like anything we've studied up to this point. Like lines, polynomials, rational functions, those will not work for certain things. Exponential functions is a new type of function that allows us to model certain things in the real world that behave a certain way, like bacteria or, well, folding. That was just so you could see it, but the bacteria is a good example. So here's the definition. Function f of x equals a raised to the x, where a is a positive number and a is not 1. is called an exponential function with base A. So exponential functions is a huge category of functions, but they all have to look like this. They all have to be a number raised to x. And the number that you put down here cannot be negative, it has to be positive, and the number you put down here cannot be 1. As long as the number here is a positive number and it's not 1, then you are looking at an exponential function. So the examples that I've given you so far are this. That is an exponential function with base what? 2. The other example I gave you was this one. That is an exponential function with base 1/2, right? You could use 0.5, that's fine. Now, 2 is a positive number, right? And it's not 1. 1/2 is a positive number, and it's not 1. So these qualify as being exponential functions. So what do these things look like when we graph them? It would be worth us looking at it. So I'm just going to summarize for you what they look like. We're not going to get into the details of why, but it's going to look like one of these two pictures. If the A we have is bigger than 1, then it's going to look a certain way. If the A we have is bigger than 0 and less than 1, then it's going to look like something else. So I'm about to draw for you what all exponential functions look like. In this case, the exponential function will look like this. So look what's happening here. This graph doesn't, what graph, does that look like anything we've looked at so far? The ones we were doing last time, right? The rational functions. Remember the rational functions had that horizontal asymptote? Okay, exponential functions do have a horizontal asymptote, but only out one side. The other side, this thing takes off and just goes and gets bigger and bigger, and it grows very rapidly. We saw that when we started plugging in different values for the bacteria, how fast this grows, right? Now also I should point out that this point right here will always be on the graph, and that's always the point 0, 1. That's the y-intercept, right? What were we getting when we plugged 0 in, right? We said if we plug 0 into any exponential function, a number raised to 0 should be 1, right? So that point 0, 1 should always be on the graph, no matter what. Agreed? From the look of this picture, do we ever have any x-intercepts? No, we do not. Okay, you do not have x-intercepts with exponential functions. They never hit the x-axis, which means this can never be 0. You can never make 2 to the x be 0, ever. No matter what x you plug in, never will that be 0. All right, so that's what it looks like if the A is bigger than 1. So see this 2 to the x? It should look like this, right? Okay, now what about this one? The A is 1/2, which means it's between 0 and 1, right? So what's the difference in the picture? What do you think the difference is? Do you have a guess? On the other side? Not quite. It actually does this. It's like the opposite. And you have the horizontal asymptote out this way. And this is basically this picture reflected over like this. Do you all see that? It'll also go through 0, 1. Still has to go through that point. So this picture right here we call exponential growth. And this one right here we call exponential decay. The idea of those two words, growth and decay, are that Exponential growth means as you move to the right, this thing grows and grows and grows, right? But this one, as you move to the right, it starts to go down. Like we were talking about, like the expected probability of something being alive or a light bulb working. This starts to decay out and starts to go towards zero, right? So exponential decay versus exponential growth. In both cases, the growth and decay happen very rapidly, right? Okay. That all right with you? So look at this example right here. F of x equals, let's say, 4 to the x. Is that an exponential function? Yes. What is its base? 4. Is that an example of exponential growth or decay? Growth. Okay? So this is a base 4 exponential function. It has its exponential growth. So if we were to graph it, it would just look like this. All I really want you to be able to do on this is just look at it and identify whether or not we have growth or decay. All right? I don't really care about you graphing these. But you should know when you're looking at a function that it's exponential and which of those two it is. All right? Does somebody want to give me an example of a decay? Just give me something to put in here. 1/3 would work? What were you thinking? No? Okay, so 1/3 to the x, would that work? The base of that exponential function is 1/3, right? And that means we have decay. So the graph of that would look like this. All right. What about this one? See if you've ever heard of this one before or seen this one before. You ever seen that before? There's a key on your calculator that has that somewhere. Let's see, who has, can I look at your calculator real quick? Yeah, okay, so if you look down, I know like you're supposed to all have the same calculators in here, but I know you don't. If you look along the left side, there's like 3 buttons down the left side of the calculator, and one of them has LN, right? And then above it in green, right, it says e to the x. You all see that? Okay, so that button's on your calculator. It's an important button. But let's talk about what this is. Is this an exponential function? Is this a number raised to x?
Yes.
It is? Is e a number?
No.
Yeah, I mean, I asked my 9-year-old daughter, she's in 4th grade. If I ask my 9-year-old daughter, is E a number, she's going to tell me that I'm crazy. She's going to say E is a letter, right? But actually in mathematics, E is a number. Okay, there's a number I'm sure you've heard of, pi. We've all heard of that number, pi, 3.1415. Pi is a very special number in mathematics, but it is a number. It's approximately 3.1415. Oops. And it keeps on going on forever, never repeats itself. It's a weird number. But E is also a number. E is actually approximately 2.718. Very, very special number in mathematics. And so when you look at this e to the x, can you tell me right now whether or not this is growth or decay? It's growth. It's growth because the base, e, is actually 2.718. And that number is bigger than 1, right? So this is an example of exponential growth. But it's a super, super important function. Unfortunately, I can't get into why, all right? And really, I couldn't explain it to you unless you were in Calculus 1. That's the first place I can actually show where its value, like where its importance comes from. So you're just gonna have to take it on faith that that is a very special function, and we use it a lot. Okay, that is, and this has a name. It's called the natural exponential function. The natural exponential function. It has to do with the reason they use natural is because it's kind of like trees. We consider them to be like nature, natural. These like they're here, right? Regardless of us, like trees are there. We went looking for a function. Mathematicians went looking for a function. We're like, we wonder if there's a function out there that has this property, and we found it. This is it. This is the one. It's just like a tree sitting there. It was there. It just naturally occurred. This is the only one that behaves that way. So it's the one. All right? It's the one. All right. Now, we're going to basically skip everything else about exponential functions now, and we're just going to get into an application of exponentials. All right? So now we just forget how beautiful they are and how important they are, and we are going to jump straight into where we use them. So this is one place we use them. This is in problems that involve simple interest. Simple interest. So I hope that you will find this somewhat valuable to you, the idea of simple interest. I'm sorry to erase you. Goodbye. Simple interest. So do y'all know how banks work? Let's talk about banks. This is a bank. Look, I'm even going to make it look like a building. Look at that. That's a bank, all right? You know how a bank works? So you have people over here. That have money, right? They have money. And then you have people over here who what? Who don't. Yeah, who need money, right? And for the most part, most Americans are in this category right here, right? You have to go figure out, like you can go buy a car, right? You go buy a car. You don't own that car until you pay off the bank, right? Yeah. You go buy a house. You don't own the house. The bank owns the house, right? Until you've paid it off. So what happens here is that these people over here say, hey, I would like to go buy this new phone, this new car, this new house, but I don't have that much money. So I'd like to, this is the way credit cards are the same way. So the bank says, all right, look, you want some money? Sure, I'll give you some money. I'll give you money. I'll loan you money as long as you are somewhat responsible. You know, we'll check your credit score or whatever. We'll give you money. So let's say that, let's take one person in particular. Let's say that this person borrows $1,000, okay? Borrows $1,000. The bank says, all right, I'm going to give you the $1,000, but you're going to owe me back that plus interest. Now, interest is basically the payment that you're going to make to them for borrowing their money. That's the charge, right? The fee, so to speak. So let's take a credit card, because I know it's easy probably to get a credit card that would give you $1,000 on it. I think that would be easy for most people to get. What is the interest rate on a credit card? Anyone know what the interest rate is usually on a credit card? 24%. That seems reasonable. Let's act like it's not that insanely high, even though it is. Let's go with 20%.
Mine is 28%.
28%? Yeah. Wow. Yeah. Okay. So this is going to be depressing. All right. So let's go with 20%, even though it can be higher. All right. 20%. Okay. So you're gonna borrow $1,000, but you have to pay 20% interest. Now, just what people seem to not realize here is that it's not that you just take the $1,000 and then take 20% of that, and that's what you owe back. It's always accumulating more because time matters. If you're borrowing the money for a long period of time and you're taking a lot of time to pay it back, that interest keeps on accumulating. And that's what this is going to be about, all right? But I just want to get us to understand the whole way the structure of this bank works. So the bank is going to loan out this money 20%. That's what they want to get back, right? Where do they get the money? From the people over here. So these people over here, they put their money in the bank, right? So their money is supposed to be sitting there, but it's not actually physically sitting in the bank, all right? That money is actually over here. You've got their money, right? That's what's happening. Now, how does it work on this end? They give you the $1,000 or whatever it is, and the bank says, hey, guess what? We are going to pay you for your money. Thank you very much for letting us borrow your money. We will give you some money back. And how much do they give back? Oh, it's ridiculous. It's like 0.2%, 0.3%, not 3%, like 0.3%. It's nothing. Now, 10 years ago, about 10 years ago, it was a little more than 10, I sold my house, and then I was building a house with my wife. And when I sold my house, I took all the proceeds from the sale and I put it into this online checking account that was kicking me back 5% interest. That was about 10, 12 years ago. A checking account that was giving me 5% interest back. That's unheard of now. Totally unheard of. Like, you can't get 5% back for just dumping your money into a checking account. But back about 10, 12 years ago, that actually was reasonable. So this is what it is now. It's like, you want to put your money in a bank, you're not going to get anything for that money, really. And then they are lending it at 20%. So how do they make their money? That difference, look at the difference. They're getting 20% back. They only are giving you 0.3%. Like, there's their profit, right? Does that make sense? Okay. It's a little more complicated than that, but that's a good enough picture, yes, to get an idea of how this works. The biggest problem that we have right now, I think, is that the United States is, you could replace this with China, and you could put this over here, the United States of America. And the United States of America is borrowing money from other countries to pay for our stuff, everything we have, roads, the government, everything, right? This deficit that they talk about, is we don't have enough money to run our government. We don't. So what do? We borrow it from other countries. They are our bank. Does that make sense? It's pretty sad. All right, sorry. All right, so simple interest. I'm going to write a formula on the board. Actually, I'm going to write two of them. First formula, A equals P, in parentheses, 1 plus R over N raised to the N times T. I know that looks complicated. Just write it down. And then the second formula is A equals P E to the R times T. These are the two most general simple interest formulas that exist out there. These two right here. And I need to explain what the difference is and what all these letters mean, because it can be complicated. So first of all, let's talk about the letter P. Does anyone know what the letter P stands for in these formulas? Principal. Now, does anyone know what principal represents? Like, when we talk about the principal of something, it's not that person you were sent to the principal over and over in school, right? It's the amount of money that you start with, okay? So this is I'm just going to put the starting amount of money. Now, this is either the amount that you're going to borrow to buy your car, or it's the amount that you're going to put into the bank so that they can go loan it out. So you can look at the principal from both perspectives, the person borrowing it or the person lending it to the bank, right? But the P is the principal, it's the starting amount of money. Now, the next thing in here, let me go with R, is what we call the interest rate. And this is always a decimal. Don't forget that. It's always a decimal in here. So if an interest rate was 20%, what would that be in our formula? 0.2, okay? Do not put 20 in there, it'll mess everything up, all right? So that's your interest rate. T here is time. And very important, it's measured in years. Bless you. I almost wrote months. We can handle months, but it's measured in years. So if you borrow money for 1 year, then T is going to be 1. If you borrow money for 10 years, T is going to be 10. If you borrow money for 6 months, T is going to be 1/2. All right? Because 6 months is half a year. So there are ways we can adjust T for like months or days. All right. What else? We have P, we have R, we have T, right? What have I not talked about? N and A. So let's do N. Well, no, let's do A, because I think A is easier to explain. A is the amount at the end of time T. So this is the amount of money. That's money. That's the amount of money at the end of the time. Okay? That's the amount of money at the end of time. So like if you go and you put your money into the bank for 2 years, you crank everything out of the formula, the answer is going to be how much would be there at the end of 2 years. It's how much money is there, all right? Or how much money you owe, whatever it is. And then the N. Okay, so the N is a difficult thing to explain, but I'll do my best. N is what we refer to as the number of compoundings per year. And this usually confuses students. So let's try and take a simple example to see if I can explain where this N comes from. Let's say I have $120. No, let's go with $100. Let's say I have $100 that I am going to borrow. What if my interest rate is 10%? How much will I'm borrowing, right? That's what I said, I'm going to borrow. How much should I owe at the end of 1 year? $110? Does that make sense? Because what's 10% of this? 10, right? So it should be $110 at the end of 1 year. That's if I were to just do the interest on this amount one time, right? One time. N is the number of times I'm going to do it per year. So what if I tell you that N is not 1, but instead N is 2? I'm going to do the interest twice. In 1 year, I'm going to do it twice. So if I did this twice, what would I get each time? I'd get 10 the first time and then 10 the second time. So you would think this would be 120 now, right? But it's not the way it works. It's actually you're going to do it twice, but you're going to do it half the percentage. So what you're going to do is 5% twice. See, that's if N is 2. Does that make sense? So you do 5% of this, let's say halfway through the year. What's 5% of that? What's 5% of that? 5. So you have $105, right? And then at the end of the year, you do 5% of that. Not of 100, 5% of that. So what would that be? I'm going to do that on my calculator. 5%, I'm going to multiply 0.05 times 105? 5.25. So now you'll have 5.25. So if I do 5% of that, I get $5.25. So if I add that to that, that'll be 110.25. All I'm trying to get you to see here is this. If I did 10% one time, we had 110, right? 10% one time, I have $110. If I do 10% broken up twice, So 5% twice, 2 times, I have $110.25. So it was actually a little better for me to break it up twice, right? What if I did n was 10? Then I would do what percentage? I'm doing 10%, but I'm going to break it up into 10 pieces. So 1%, right? But I'm going to do it 1% 10 times. And that number will be a little bit bigger. A little bit bigger, not much. All right? Does that kind of make sense what this number represents? It's the number of times you're going to compound the interest per year, but you do it on a smaller percent. So you take your overall rate and cut it up. So it doesn't have a huge impact, but it does have an impact. All right. So you ready to do a problem? Let's do a problem with these formulas. Oh, and what's E? 2.718. Okay, it's that special number, all right? I like to do lottery examples because it's really kind of mind-numbing. All right, so let's say that you win the lottery, okay? Let's say you win a lottery. How much do you want to win in this lottery? And don't be crazy. Don't be like the one who wins the 500, 600 million. Let's do something a little more reasonable. How much? 3 million. After taxes or before? Before taxes. So if you win $3 million in the lottery, you're probably going to walk with about half of that. Okay? So let's say you just got a check from Lotto for $1.5 million. All right? What we plan to do, let's just see what happens if we just take that money and put it into like some sort of savings bond or something like that, where we're going to put the money away. We're not actually going to touch it for a year. Right? We're just going to do 1 year at a certain percentage, at a certain rate. All right? So how much would you have after 1 year? I don't know what savings bonds or CDs rates are right now. Anyone know? I doubt it's very good. 1 year?
1%.
It's 1%-ish? Yeah, let's do something that is a little bit better. Let's go with like 3.2%. So how much would you have after 1 year if invested at 3.2% interest rate? Okay, and now the next thing I need to ask you 2 separate questions. I think I'll erase these. So I'm going to have a part A and a part B. How much would you have after 1 year if invested at 3.2% interest rate? Part A, if compounded monthly. And then part B, if compounded what we call continuously. Now, I haven't explained this. I'm about to explain it, all right? And then that one monthly, we'll just go through each of these. So let's look at part A. We're going to put our $1.5 million into some investment. We can't touch it for a year. And I want to know how much we're going to have at the end of that year if it's 3.2% interest, all right? If the interest is compounded monthly, that means they're going to calculate our interest 12 times, aren't they? But they're going to do it on a smaller percentage of our rate each time. And then compound it continuously. We'll talk about that when we get to it. So for this one, which formula do I use? Because I said there was 2 of them, right? on this one, because it says monthly, that means that n is what? N is the number of compoundings per year. So what would n be? 12. Okay, which of the two formulas that I gave you had n in it? The first one, right? So we use that formula. We're going to use A equals P, parentheses 1 plus R over n raised to the n times t. So all we have to do now is just plug everything we have into this formula. And I'm going to erase part B and come back to it. All right, so let's plug in. The amount that we have will be, what's our principal? What's the amount we're putting in? 1,500,000, right? And then we have 1 plus, what is our interest rate? So 0.032, right? That is 3.2% written as a decimal, divided by what? Divided by n. What's n? N is the number of compoundings per year, which is given to us by that monthly. So this should be 12. And then raised to the n, which is 12, times t, which is 1. Right? Everyone understand where everything came from here? All right, the way we do this, let's do order of operations. We're going to do what's in parentheses first, right? And within here, we have addition and division. So we got to do this division first. So on your calculator, do 0.032 divided by 12. And you want to go out as many decimals as you can with this. You're going to get some crazy thing. Now, once you do that, add 1 to it. Just add 1 to that answer. And so we'll be here. So this becomes 1.00266. How many sixes do you have?
5 and 7.
Okay, so just go out as many as you want, all right? Just don't round it to 1. Don't round this to 1, okay? This is not 1. The more decimals you have, the more accurate this answer is going to be. I'm just going to stop there. Now I have to raise this to what power? 12 times 1 is 12. So again, order of operations, be real careful here. Do not multiply these together. You must do this to this power first. So take that answer, 1.0026666, raise that to the 12th. And the number's not going to change much. 1,500,000 times 1 point, I'm getting 1.0324735 something. Okay, so we might all be off a little bit here rounding. It's okay. Now take that number and multiply it times that. Times the 1.5 million. And you should get 1,548,710. I'm getting 0.17. Look, we can be off by $1. It's okay. That's going to be rounding. Anyone else get something close to that? Does everybody have 1,548,710 or no? Yeah? So how much is there after a year? How much did we make?
$48,000.
We made $48,000 off our money. Right? Just by having that money sitting there, we made almost 50 grand a year. Just by having it. Right? Now we weren't allowed to touch it, but we could take that 50 grand and do whatever we want with it, right? And the next year we would have the same thing. So what would happen if you locked this money up a little bit longer? Or let's do something else. What if you invested in the stock market? So the stock market, it depends on how you invest. You can have much better returns than this.